Hi, I'm Yang Jin, and I was responsible for Task 1, which includes both Part A and Part B. For Task 1A, I implemented the test and set function. The idea is simple but powerful. It automatically sets the log to busy and returns the old value. If the old value was false, that means the log was free and I successfully accepted it. If it was true, that means someone else already had the log. I use C++ with this because it was directly uh, shows the hardware instruction and automatically. For text 1b, I built the release function around that test and set. A queue keeping called test and set log until it's written false, meaning the log was free and now I own it. Let's just set the log back to false so another third can get in. Then wrote a program with 5 thirds. Each third tries to enter the section, prints its ID once inside, sleeps for a short random time to work, and then calls release. When I run the program, the output shows that only 1/3 was inside the section at a time, even though all 5/3 want to enter. Yeah, this one. They had to wait for return. That's how test and set ensures until only 1/3 can flip the log from free to busy, and the other keeps until it's released. I also explain why busy waiting is uh, inefficient. Well, 1/3 is inside the section, the other 4/3 are stuck in a loop, constantly checking the log and the CPU cycles without doing any useful work. The waste resource and doesn't, well, the section takes longer. That's why later text use that with proper blocking instead of busy waiting. So overall, my part proves that test and set works for uh, mutual, but also shows the downsides of busy waitings, which set the stage of text 2.
Hi, I am Chen Yuhan, and I was responsible for Task 2A, which is implementing a counting semaphore with FIFO fairness. So the goal of Task 2 is to implement a counting semaphore using Python, allowing up to 3 concurrent threads to efficiently manage resources without busy waiting, employing a block mechanism instead. So I create a custom semaphore class in Python. It starts with a value of 3 as we can see it here. Yeah, initial equals to 3. And meaning there are 3 threads can enter the critical region at the same time. So let's go to next page. The counting semaphore, in this counting semaphore, it employs a wait function and also a signal function. These two operations make sure that it can regulate access and maintain order among threads. So if a thread calls the wait function and the value is greater than 0, it decrements the value and enters. If the value is 0, the thread is blocking and placed into a FIFO queue. Then in signal function, if there are waiting threads, the next one in the queue is woken up. If no one is waiting, the value is incremented. This ensures strict FIFO fairness. Threads are served in order they arrived, so no one gets starved. Just like in this picture, the FIFO fairness maintains a structured queue processing requests in order of arrival. This approach prevents starvation, guarantees that all threads are served, and ensures predictability in resource allocation. So the attributes and operation explained is that the semaphore class includes attributes for managing the resource pool and the mask for wait and signal operations, ensuring proper control over the concurrent thread access while maintaining FIFO fairness. And also I'd like to explain one question about the task 2. Why we need a counting semaphore instead of a binary semaphore. So the reason is that a binary semaphore only allows one thread at a time, but here the assignment requires up to 3 threads in the critical region. Simultaneously, when I ran the program with 5 threads, the output showed that only 3 threads were inside the critical region at once, while the other waited as soon as one exited. The next waiting thread was woken up in FIFO order. That proves mutual exclusion and fairness are working correctly. Yeah, that's all. Thank you.
Hi, I'm Habibullah Zamani and I will explain task 2b, which is demonstrating mutual exclusion with 5 threads using the counting semaphore. I reuse the semaphore class from task 2a, which starts with a value of 3. This means only 3 threads can be inside the critical section at the same time. I then created 5 threads and each one tries to enter by calling the wait function. If the semaphore has a free slot, then the thread enters and prints its ID. If not, the thread is blocked and placed into the FIFO queue. Inside the critical section, each thread sleeps for a short random time to simulate work, then calls signal function to exit. When a thread exits, the next waiting thread in the queue is woken up in FIFO order. During the program, the output clearly showed that only 3 threads were inside at once, while the others waited. As soon as one exited, the next waiting thread entered. This proves that the counting semaphore enforces mutual exclusion with up to 3 threads and that FIFO fairness prevents starvation. So my part demonstrates how the semaphore works in practice, ensuring both mutual exclusion and fairness among the threads.